Hello. So this is the end of the section 1.7 and 1.8 notes that we didn't get to today. So this is where we left off. We were talking about sizes of ions. So next we have the concept of isoelectronic ions, and things that are isoelectronic means they just contain the same number of electrons. And usually atoms will form ions, so they become isoelectronic with the nearest noble gas, and they do this to become stable and have a full outer energy level. So in this example right here, we have O2, O negative 2, F negative 1, and then sodium positive 1, magnesium positive 2, and aluminum positive 3. Now all of those ions are isoelectronic with neon. They all have the same number of electrons as neon. And the negative ions gained electrons to get up to the number that neon has. Neon has 10 electrons total, as 8 in the outer energy level. And 8 is the key. That means it's stable. And then sodium, magnesium, and aluminum, they all lost electrons to become isoelectronic with neon and become stable. So when we want to compare these ions in size, you always want to consider the number of electrons and the protons. So with the electrons being equal, now really all we have to look at is protons. So the stronger, the greater the number of protons in the nucleus, that means you're going to have a greater nuclear attraction for the electrons. So the charge is going to increase, so that means you're going to have a stronger Coulombic force pulling the electrons in closer. So that means it's going to be a smaller size. So when you're comparing isoelectronic ions, you just want to look for the ion that has the most number of protons. So aluminum with 13 is going to have the greatest number of protons, so it's going to be the smallest of this bunch. Then magnesium is the next smallest, then sodium, then fluoride, and then O negative 2, that's going to be your largest ion. So look for the number of protons, and the greatest number of protons is going to be the smallest ion when you're comparing isoelectronics. Right, so a couple of practice problems here. Predict and justify the periodic trends in radius for the following ions. So in this first bunch, they're all positive 2. So all of these ions are in the second group, the alkali earth metal group on the periodic table. They all form positive 2 ions to become stable. So this is just a group trend. So the order in which we go is going to be beryllium, then magnesium, then calcium, and then strontium is going to be the largest. And the justification is just the same as atomic radius. As you move down a group, the shielding effect is increasing, and you're adding energy levels or layers of electrons. The second one is predict and justify the periodic trend in radius for the following ions: potassium +1, calcium +2, sulfide -2, and chloride -1. So this is an example where all those ions are isoelectronic, and they're all isoelectronic with argon. So you want to order them. The largest one is going to have the fewest number of protons. So that's going to be the sulfide ion, and then chloride, and then potassium, and then calcium positive 2 is going to be the smallest one because it has the most number of protons. And here's the answers again. You can pause it and copy this down if you want. I listed them from smallest to largest for both of those. Okay, the next periodic trend is electron affinity. Electron affinity is defined as the energy change associated with the addition of an electron to a gaseous atom. And the trend is it increases as you move up and to the right, but we don't include the noble gases in this trend, right? So the idea with electron affinity is atoms that want to gain electrons to become stable, which are the nonmetals, they tend to have a higher electron affinity. So when they gain the electron to become like a noble gas and have the octet rule, they're going to give off some energy. So the atoms that are closer to this, like fluorine, chlorine, they really want to gain electrons to become more stable. So they're going to have high electron affinities. Electron affinity just means they want to gain electrons to become stable. So nonmetals tend to have high electron affinities, and metals tend to have really low electron affinities because they don't want to gain electrons, they want to lose electrons to become stable. Another thing is if an atom or ion is already stable, then they have low electron affinities. So once something becomes stable, has a full outer energy level or octet rule, then they're not going to want to change. So they don't want electrons, so they have low electron affinity. Next is electronegativity. Electronegativity is the ability of an atom and a molecule to attract shared electrons to itself. This happens when they're in compounds. And the trend here is it increases as you move up and to the right. And this is another case where we don't include the noble gases in the trend. So F is the largest electronegativity. Now electronegativity has values associated with it, and we'll learn those later, but fluorine is the largest with a value of 4. And then it tends to just decrease as you move down and to the left. So it helps if you remember fluorine being the largest, and then so as you move away from fluorine, the electronegativity decreases. And we use electronegativity a lot when we're talking about polarity of bonds and molecules, which we'll get into in the next unit. Right, and then another thing with periodic trends, we can use periodicity. Periodicity just means placement on the periodic table, really. So we can use that to predict values of properties in the absence of data. So if we're not sure about some property, it could be like melting point or boiling point or density or really any physical property, physical or chemical property, we can use the periodic table as a way to make estimations. Okay? So with this, we just use the placement on the periodic table. So the example here is sulfur has a melting point of 115.2 degrees Celsius. Tellurium has a melting point of 449.5 degrees Celsius. And we want to estimate the melting point of selenium. Okay, well, if we look on the periodic table, we're given sulfur and we're given tellurium. Sulfur is S, tellurium is Te. We're asked to find the melting point of selenium, Se, which is in between. So the way you would do this is just figure out a halfway point between sulfur and tellurium, and that would be a good estimation for selenium. So in this, we don't have to do an exact calculation, just an estimation. So what I would do is I would just say, well, sulfur is around 100, tellurium is around 450, so that's a difference of 350, so about halfway is 175. So I would just add 175 to sulfur, and that would be a reasonable estimation for selenium. So 100 plus 175, that would be 275 degrees Celsius. Okay? So you don't have to get exact numbers. This is just used for estimating. So estimate, don't calculate. Okay, there's a periodic table. We'll get back to that. Okay, so topic 1.8 now is on valence electrons and ionic compounds. So first of all, we want to know the number of valence electrons for a group and the ionic charge that the elements in that group tend to form. So let's go back to that periodic table. So just to review, well, for valence electrons first, this first column, the alkali metals all have 1. The alkali earth metals all have 2. The D block and the F block, you could really say that they have 2 valence electrons, but they do some different things. So don't worry about that so much. This boron group has 3 valence electrons. Carbon group has 4 valence electrons. Nitrogen group has 5. The oxygen group has 6. The halogens have 7. And the noble gases have 8, except for helium, which only has 2. Okay. And then the common charges that they tend to form, the alkali metals tend to form +1, alkaline earth metals tend to form +2, so they lose electrons to become like the noble gas behind them. The transition metals do some different things with their d electrons, so they don't have set rules, except for zinc, which forms a +2, and silver, which forms a +1. Aluminum forms a +3. The carbon group tends to share electrons rather than lose or gain. So they tend to not form ions. The nitrogen group tends to form -3. So the nonmetals are going to be gaining electrons to get up to a noble gas now. So the nitrogen group is a -3. Oxygen group, they form -2s. And the halogens form -1s. And our noble gases, they're already set, so they don't do anything. Okay, and then we also have elements will lose or gain electrons to achieve the same electron configuration as the nearest noble gas. They want to have 8 valence electrons. That makes them happy. They're stable when that happens. And an 8 of anything is called an octet. So this is called the octet rule. Elements in the same group will tend to form analogous compounds with similar physical properties. So the example right here deals with that situation. So we want to list a compound similar to K2Se. So when we list a compound similar, you would expect that compound to have similar physical and similar chemical properties. So really what you want to do here is look for the elements directly above and below the elements that are already in the compound. So with potassium, the element above potassium is Na, sodium. And the element directly below it is rubidium, Rb. So you could substitute in sodium for potassium, and that would be what's called an analogous compound. So it would be Na2Se, or it'd be Rb2Se. The thing that has to stay the same is the 2-to-1 ratio between the metal ion and the non-metal ion. With selenium, you can substitute in sulfur, which is right above it, or tellurium, which is right below it. So you could have K2S. That would be an analogous compound. Or you could have K2Te. That would be another analogous compound. And you would expect those compounds to have similar properties. So here's a list of analogous compounds. So I listed several of them, but really it's any combination of those positive ions, K, Na, and Rb, with Se, S, and Te in a 2-to-1 ratio. And that's all for the Unit 1 notes. Have a great day.